Good evening, everyone. It's nice to see so many familiar faces. Thanks for coming out to Brian Switek's lecture. We're just thrilled to have him. Before I introduce him this evening, I wanted to tell you about a couple other exciting events that we have going on at the museum this month. The first is this Saturday, Catherine Coles, who is the former poet laureate of the state of Utah, is going to be doing a reading and discussion from her new book called The Earth is Not Flat. Catherine Coles had an amazing opportunity to go to Antarctica as part of the NSF-funded Antarctic Artists and Writers Project. And the goal of the project is to bring artists and scientists together in this extreme environment so that artists and scientists can explore what these different disciplines can offer to each other. And so if you've ever heard Catherine Coles speak, she's just an amazing storyteller. She was gracious enough to speak after one of our science movie nights this spring, and the stories about how she had to prepare for the journey, her incredible penguin summoning capabilities, the mountains that moved across the landscape throughout the day, in addition to the process of writing poetry and her interactions with the scientists are just wonderful, wonderful stories. So she'll be speaking here this Saturday at 2 o'clock here in the forum. She'll be reading some of the poems from this book that was inspired by her experiences in Antarctica, and then talking about her experiences and answering your questions. So a lovely way to spend a Saturday afternoon. I hope you can join us for that. And then, as many of you know, we bid a fond adieu to Weaving a Revolution, our Navajo basket exhibit, at the end of April, and are now preparing for the launch of Nature Unleashed, our next special exhibit that comes to us from the Field Museum in Chicago and looks at the science behind natural disasters, as well as the human stories. So plan to join us on the 25th if you're not traveling for Memorial Day or soon thereafter to explore Nature Unleashed. So this evening, we're thrilled to have Brian Switek. Many of you know him as a paleontology volunteer here at the Natural History Museum of Utah. I see lots of the fan club here. But he is also an illustrious writer, freelance science writer, author of the acclaimed book Written in Stone, as well as this new book, My Beloved Brontosaurus. And he also blogs currently for National Geographic in his Laylops, am I saying it right? blog. He's also blogged for the Smithsonian and been published many other places, and brings with him a deep-seated passion for all things dinosaur. So I think with that, I'll go ahead and turn it over to Brian. Will you join me in welcoming him tonight?
Well, thank you for coming out tonight. It's great to see an excellent turnout for this. And I feel like I've been waiting to give this talk for almost my entire life. This is me, about five years old. Not much has changed in terms of my enthusiasm. Most photographs I have of me now are still me making this face in front of dinosaur skeletons, things at museums. But that's the great thing about dinosaurs, is they're really, an immediate entree not only into prehistory and evolution, but into science and the way science works. It's a way to immediately, plug into the natural world and start asking, many questions about, what were these animals like? How long ago did they live? What colors were they? I kind of feel bad saying this with this slide up because that is not actually a dinosaur. That is a pterosaur. It's a related flying animal. Yes, I saw someone recognize this in the back. I'm glad I caught that before someone asked an awkward question later on during the presentation. But that's the thing. It's looking through these monstrous animals. It's a way to really put our own existence sort of into context by asking and answering these questions about how these animals actually lived. We end up sort of asking and answering questions about ourselves. But for me, it wasn't the pterosaurs. It wasn't even Tyrannosaurus Rex that really got me. It was Brontosaurus, the so-called thunder lizard, this Jurassic titan that really just captured my imagination. This was my favorite dinosaur book as a kid. I think might have been one of the golden books, I'm not sure, but just seeing this illustration and the illustrations within, it really closely matched the skeleton that was on display at the American Museum of Natural History. This is the mount as it was originally put up a bit before my time, but it was still in this general position and still had that stupid blunt skull at the end of it when I first saw it in about 1988. And I couldn't help but wonder about what this animal sounded like, how it moved, what the environment was like. It was impossible to look at these vestiges of ancient life and not start plugging in to these queries that people have been puzzling about for centuries, before there's even a word for dinosaur. When people in China and India and ancient Greece and Rome, Native Americans would find bones tumbling out of the rock, and they wouldn't correspond to any animal that they knew of, and they would come up with stories and myths and legends about heroes and monsters and griffins and giants and all these other sort of creatures that lived during this ancient past before there were any people around. They didn't have a name for what these animals were. They didn't really understand what dinosaurs were, but they realized that this was something from the Earth's own past, something to sort of plug into and measure our own existence against. And beyond that context, dinosaurs are just really cool. I mean, they're awesome. They really are. This is a sort of diagram that gives you some idea of like the scale of these animals that we're looking at. I mean, obviously we can see this when we go into museum halls, like the one right downstairs. But that little blob on the bottom to the side there, that's a human skull compared to a giraffe, compared to an ostrich. So even these so-called long-necked animals today, nothing compared to Supersaurus and Diplodocus and these other sort of sauropod dinosaurs. And just seeing that scale, it's like, how could anything that large possibly have existed? Something that, I didn't know about this research when I was a kid, but if I did, I probably would have gone bananas when I found this out. There's something called the recurrent laryngeal nerve. This is a feature that is shared within all land-dwelling vertebrates and the descendant creatures that have gone back into the ocean, things like dolphins as well. And it's a nerve that goes from the brain into the throat, and it goes into the larynx, and it sort of controls various aspects of the throat. But rather than taking a direct route, which would be relatively short, it loops down around the aortic arches of the heart, and it goes back up again. So it's twice as long as it has to be. So in the diagram of a human, that's not necessarily very impressive. I mean, it's a great example of unintelligent design. Any engineer would be an idiot to kind of create this sort of system. But think about this, not only in a giraffe, but in something like Supersaurus or one of these giant dinosaurs. For a 30-foot neck, you'd need 60 feet of nerve to make this simple connection that isn't really, it doesn't need that much at all. So just thinking about just the biology of these, I mean, this is something that hasn't been directly found in the fossil record, but we know from evolutionary logic must have existed in these animals. And to learn these basic facts, not only that these things existed, but these ideas about how they live, these little intricate aspects of their biology, it's absolutely wonderful. I mean, I'm really glad that Dinomania is not only continuing, but really being spurred on by these kind of findings now. But for me, the difficulty in all this was that there weren't many dinosaurs in the immediate area where I grew up. I wanted to be a paleontologist so badly, so very badly, and what my parents, what my guidance counselor, and what everybody else said was, well, you don't live in Montana, you don't live in the Dakotas, you need to go to the Badlands if you want to study. There are no dinosaurs in New Jersey. Just, forget it. Like, this is an actual photograph of the site where one of the most important dinosaurs ever found, called Hadrosaurus, was actually found in southern New Jersey. This is a rather flattering photograph. I've actually been down in here. It's filled with garbage and muck, and it's at the end of a cul-de-sac that has been built over. So one of the most pivotal sites in American paleontology is celebrated just by a little plaque and a couple of plastic dinosaurs basically by the side of the road and an ongoing development. So I knew if I, through my ongoing love of dinosaurs, if I wanted to study them, I had to get out west. I had to go somewhere where they weren't being paved over or otherwise kind of thrown into the trash heap. And that didn't happen until 2009. So I kept the Dinomania going in my own life through reading papers and watching the Jurassic Park movies ad nauseum, and just trying to find dinosaurs wherever I could. But in 2009, as a way to sort of convince me to move out west and to move to Utah, my wife organized a trip out here, and on the third day, we woke up in Dinosaur National Monument, the Green River Campground. Many of you are probably familiar with this scene if you've been out there, and I woke up and I saw the sun hit this formation is actually pre-dinosaur during the Permian era, but just seeing this and seeing the landscape, seeing this iconic place in paleontology, I instantly like, yeah, I have to be here. I have to be here like yesterday. So within about 2 years, I made that happen. And now I spend my time imagining scenes like this. This is a restoration of what Dinosaur National Monument might have looked like, during the heyday of the Jurassic era. So this is the environment in which that famous quarry wall was laid down in. It's the age of dinosaur giants and just an insane ecosystem, unlike anything we're familiar with now. And it goes beyond those classics. This is another dinosaur many of you are probably familiar with. This is a restoration of Camarasaurus, and this is just one of 8 dinosaurs that were named from fossils found in Utah the very year before I came out here. So it's a friend of mine, when he came and visited me out here, he once asked me, like, haven't we found all the dinosaurs already? I mean, people have been looking for these things for well over a century. We've got Tyrannosaurus, we've got Alamosaurus and Diplodocus and Stegosaurus, and all the famous ones isn't the catalog basically full? And the fact is, no. Not only were there 8 species named the year before I came out here, there are several more that are still impressed. There are many more that have yet to be discovered. And it really seemed to me that Utah was the place to come to if I wanted to chase down dinosaurs. I mean, part of the reason for that was because during the 19th century, during the classic Bone Wars era that really opened up the American West, you had 2 dueling paleontologists that I'll get to in a moment as part of a story about what happened to Brontosaurus. But you had Othniel Charles Marsh, based out of Yale, and you had Edward Drinker Cope, based out of Philadelphia. And their main quarries were in Wyoming and Colorado and elsewhere in the West. They both, or at least Marsh, passed through Utah, and he picked up a couple dinosaur teeth, and they named a couple scrappy things. But Utah was generally untouched. It was generally looked over during the dinosaurian heyday. It was only during the 20th century, and really over the past 30 years or so, that people have started to realize just how wonderful and how complete the dinosaur record is here in Utah. And what I didn't really even realize until I got here was that the death of Brontosaurus, the death of my most favorite dinosaur as a kid, can be drawn back right to Utah. So this is the skeleton as it is now. This is the modern image of the dinosaur that we call Apatosaurus. But the critical piece of this that made the difference between Brontosaurus and Apatosaurus is that skull, and that skull can be drawn back to Dinosaur National Monument. So here's Cope and Marsh. That's Cope there on the left and Marsh there on the right. I'd like to call these guys gentlemen, but based upon their comportment with each other, I don't think that's necessarily accurate. They started off as friends, very, very quickly turned into scientific rivals. They would work so quickly as to send in scientific descriptions by telegraph, so they'd beat the other one into press. And like any scrap of dinosaur bone, that could possibly be a new species, and they're vying with each other to be the vertebrate paleontologist in the United States, because that wasn't really a job before. I mean, Marsh's position at Yale was the first academic paleontology position that there was in the country. So these guys were really the pioneers of their time. We're carrying on their legacy now. And it's important to mention them because Brontosaurus, animal that we now call Apatosaurus, is a Bone Wars era dinosaur. So in 1877, there was a field worker named Arthur Lakes, and he actually did this illustration. He fancied himself as an illustrator as well as an amateur paleontologist. Working in Colorado, he found the bones of a long-necked, heavy-bodied, long-tailed dinosaur. And these went over to Marsh. Marsh named this animal Apatosaurus ajax. Lakes was good enough in the field that Marsh kept him on. He sent him to another quarry in Como Bluff, Wyoming, where just about a year or so later, Lakes and his colleagues there found the bones of another long-necked, heavy-bodied, long-tailed dinosaur. These got sent to Marsh as well, and these were called Brontosaurus excelsus. So very, very similar dinosaurs, but Marsh thought that they were different enough from each other to deserve totally separate names. And these are the earliest illustrations of the animal that Marsh would end up calling Brontosaurus, but we call Apatosaurus now. And these were only done on paper. It wasn't until after Marsh's death that you could go to museums and actually see these skeletons put up, because Marsh and paleontologists of his time thought it was sort of vulgar to put up dinosaur skeletons for the public. The public would kind of get their grimy mitts all over his precious bones, and that couldn't be allowed, so they only reconstructed them or restored them in pen and ink. I'm certainly glad that that trend has changed. And you actually see the bones of this animal at Yale now. I mean, I think it was in the 1930s that Brontosaurus skeleton, that one that's towering over the rest, got put up at the Yale Peabody Museum. And the bones are still standing there as they did at that time. They've been sort of locked in that position for almost a century. People tend to call this scene, dinosaurs waiting for an elevator, very stock still and sort of stiff as if they're waiting to, get the lift out of the hall. But the critical aspect that, made Brontosaurus disappear was a revision done by the gentleman here overseeing the excavation of a giant sloth pelvis. His name is Elmer Riggs. And in 1903, he went back to these sauropod skeletons. And he said, well, they're not really different. They're different species, but they're not really different enough to deserve different genus names. So Brontosaurus should be sunk. It was named second. Apatosaurus has priority. So now we've got two different species of Apatosaurus. And this was 1903. Brontosaurus should have been dead by then, but it persisted for decades. I mean, that's the dinosaur that I met when I went to these museums. And a lot of its identity was wrapped up in its skull. Now, this is the skull of a dinosaur called Camarasaurus, a dinosaur that lived during the same time, another 150 million-year-old classic Morrison formation dinosaur. And Marsh and a lot of his colleagues thought that that Camarasaurus and the animal formerly called Brontosaurus were very, very similar. So being that the Brontosaurus and Apatosaurus skeletons lacked skulls, it only seemed natural to devise something like this to put on the end of it. So this was the Yale rendition with an interesting kind of snout going on there. This is the American Museum of Natural History rendition, my favorite one. And then the Carnegie Museum in Pittsburgh also did their own, although they only put a head on it when they learned that Riggs was coming to look at their dinosaur skeletons. They left their skeleton headless for about 3 decades just because they didn't want to get drawn into this sort of scientific speculation about what it looked like. It was really only a couple of years after Riggs did this revision that the skull actually was found, but it took this really circuitous route into publication. So this is Earl Douglas standing in front of the old Quarry wall at Dinosaur National Monument before it became a national monument. So in 1909, Douglas was looking around the hills on the near the Utah-Colorado border, and he found this fantastic bone bed. I mean, the museum just opened again, I think about a year or so ago, so you can actually go and see this again. But it's this wonderful log jam of Jurassic dinosaur bones. And within this sort of jumble of Jurassic dinosaurs, he found a lot of skulls that look like this. This is a skull that's actually from another site called Bone Cabin Quarry. It's a skull of a dinosaur called Diplodocus. And very, very different from Camarasaurus, not as blunt. The teeth aren't spoon-shaped, this elongated sort of skull with pencil-like teeth. But not all of them were exactly the same. Some of them were a little wider, some of them were a little bit bulkier. And he started wondering, well, are all these Diplodocus skulls? Maybe I'm finally finding, the Brontosaurus or Apatosaurus skulls that have been missing for so long. And his boss back at the Carnegie, William Holland, thought he was right, but Holland never really went forward with this. The skull, this wider skull that Douglas had found, got labeled Diplodocus, put into storage until 1975 when a physicist turned dinosaur expert named Jack McIntosh actually went back into the collections and found it had been sitting there for about 7 decades. And finally, at long last, in 1975, you can see sort of the difference in the skull. You can see why it was so confusing for so long. I mean, really, outside of the bulkiness, these animals are closely related, very, very similar skulls, but all the same, different. Mystery is finally solved, and that is what finally allowed Apatosaurus to sort of come to the fore, for Brontosaurus to be sort of ushered off the stage a little bit, and the new image of dinosaurs to come through. And with that, this was during the time of the Dinosaur Renaissance, when paleontologists were giving dinosaurs this major, major overhaul, saying, okay, they're not gigantic lizards. They're not just huge crocodiles. They're not as slow and stupid and swamp-bound as we thought. These are animals that walked around with their necks and their tails lifted high. Were much more bird-like in a lot of ways than anyone had ever previously expected. So you went from that classic image of tail dragging, moronic Brontosaurus wallowing in the swamp to something much more like this, or possibly even like this. I mean, this is entirely speculative, and some people will groan when I show them this image, but it's entirely possible based upon the distribution of fluff and fuzz and bristles that paleontologists are now finding among dinosaurs, that some of the really iconic ones, like Apatosaurus, might have been fluffy. It's no direct evidence has found this yet, but they might have been cuter than we ever actually imagined. I mean, who wouldn't love that? And a lot of the finds, a lot of the new discoveries that are getting me excited are actually coming out of Utah. I mean, I did move here after all for the paleontology. This is a view into the Jurassic Morrison Formation from the Hanksville Burpee Quarry. And just the bones are coming out of this site, and others are giving us more information about prehistoric lives than we've ever really had before. And Utah is really spectacular. I mean, it's a little bit hard to see because it has to be so condensed, but almost the entire reign of the non-avian dinosaurs is contained in Utah rocks. We can track it from basically the very beginning, almost to the very end. That's starting, with early dinosaurs like this. This is Coelophysis, so these animals that really kicked off what we think of as the age of dinosaurs, all the way through Tyrannosaurus Rex itself. The Tyrannosaurus Rex is found in Utah. And yes, T-Rex too probably was a little bit fluffier, fuzzier than we often like to imagine. But dinosaurs didn't start off in charge. So if we think about the beginning of the age of dinosaurs, we like to think that dinosaurs sort of tore onto the scene immediately, and they took everything else over, and their dominance began like 225 million years ago. Well, the fact of the matter is, during the Triassic, during that first major era of dinosaurs, it was croc cousins that actually ruled the world. So it was animals like this. This is a phytosaur. So if you go to sites like those in Lisbon Valley or in New Mexico, in Ghost Ranch with the museum crews, find quite a bit of these very crocodile-like animals. They're not true crocodiles, but they're close relatives, and they're crocodiling before they were true crocodiles as we know them today. We also find things like this. This is what scientists sometimes call an armadillodile, or the official name is Aetosaurus. So these almost reptilian versions of an armored pig snuffling around through the Triassic undergrowth. And also creatures like this that are imitating dinosaurs in a way, or at least through convergent evolution, are very, very similar, holding their legs beneath their body, running around probably on two legs. This is something called Postosuchus. This is probably the most terrifying animal of its day. And during this time, dinosaurs are relatively small. They're relatively marginal in the environments in which they existed. They're hunted by animals like this. And it wasn't until the end of the Triassic that a mass extinction event wiped most of those croc lineages away and kind of gave dinosaurs their major shot. And that's when we get into sort of what we typically think of as the major age of dinosaurs. And in Utah, we've got this in abundance. This is a track from a limping theropod dinosaur just outside Arches National Park. There's, I forget the mile marker, but if you turn off the road and you follow it back, you can get to this track site and follow the tracks of an animal that apparently had been injured. So some of the strides are long and some of them are short. So this is an animal that had some kind of pathology, and this is behavior in the fossil record. I mean, tracks might not seem as sexy as bones, but these are moments in time that are fossilized. This is something an animal actually did. Of all the Jurassic sites that we've got, it's probably this one that might be most famous or most productive in terms of what remains in Utah in our collections here. This is the Cleveland Lloyd Dinosaur Quarry just outside of Price. And I'm sure many of you have seen the exhibit downstairs. There are over 46 individual Allosaurus that have come out of this quarry. Bits and pieces of them. There are probably many, many more. I mean, that's probably a significant underestimate of how many of these dinosaurs there were. And that's pretty spectacular because even though there are many other dinosaurs found at this site, it's totally dominated by these predators. Why is that so? And why, out of all these, was Allosaurus the most common on the landscape? So, you've got Allosaurus as the big major predator, something that you certainly wouldn't want to rub the wrong way. But you've also got this animal, Torosaurus, which got as big, if not larger. You've also got a particularly large variety of Ceratosaurus. If you go to almost any other museum, the Smithsonian Museum in Washington or the Carnegie Museum, their Ceratosaurus specimens are relatively small. They're about the size of a German Shepherd or maybe a little bit larger. If you go downstairs and you look at ours, this is particularly giant compared to, so you've got at least 3 species of giant carnivorous dinosaur, plus the mid-sized one. This is Marsosaurus from our exhibit downstairs as well. How in the world did they all survive alongside each other? How did they sort of partition the ecological space between them? I mean, they can't all have Bronto burgers for lunch every single day. They have to be doing something different. And this is one of the reasons why I love Utah paleontologists, because these are all classic dinosaurs, and we've got many of these bones here in our own collections. They form the basis of a major and very important research collection into this animal. I mean, you'd think that, okay, once you've got one Allosaurus, that's enough. We've got, the entire animal. But by collecting bones from multiple specimens, you can get an idea about, variation, about how these animals grew cut into bones to get information that we wouldn't otherwise get because we have so many doubles to sort of work from. So by using all that, maybe we can start to finally answer some of these questions about an ecosystem that there's no modern equivalent of it. I mean, the closest thing might be something like the African savanna, where you've got multiple varieties of carnivorous animals and even more herbivorous animals living side by side, but at a scale that's never been seen. I mean, you've got Apatosaurus and Diplodocus and Barosaurus that are 80 feet long, plus being chased by predators that are 30 or 40 feet long, and then all the smaller varieties of dinosaurs. Well, how did this actually work as an ecosystem? That's something that's not entirely been resolved yet, and that's one of the things that's great about Utah Paleo, is that it's not as if we're finding sort of these static monuments that we just dust off and we put on a shelf and then it's done. Everything that we find opens up these sort of new mysteries. So moving on through the column, I mean, there are bits here that I can't even fully address in this talk because there's so much being found, especially in the Cedar Mountain Formation, so the slice of early Cretaceous time that our state paleontologist Jim Kirkland does a lot of work in. It's 30 million years that new dinosaurs are being named out of this particular formation at an astonishing rate. But the really exciting part, and the part that this museum itself has played a major role in, is in dinosaurs that are being found in Grand Staircase Escalante National Monument. Now, finding a new dinosaur by itself is pretty cool. It's something that's never been seen before. But it's not just like a one-shot discovery. It's not something that we just kind of then put aside and say, okay, we know that animals are restoration, it's all done. Finding these new species are unlocking patterns in ecology and evolution that we never expected before. So many of you are probably familiar with these dinosaurs. This is Utahceratops and Camarasaurus from the paper that named them, I think, in 2010. And these animals, they're similar to dinosaurs that have traditionally been found further north, but they're different genera. And they fit into this major pattern of dinosaur evolution, that there seems to be this split that's happening between north and south. So if you look at the top, you have a lot of varieties or a lot of species of a particular dinosaur around 76 million years ago called Camarasaurus, and that's Bagaceratops with the V. And if you go to the south, you're getting Utahceratops and Pentaceratops and Agujaceratops and Camarasaurus. So these very different animals, and there seems to be this break between them. There seems to be this sort of almost island on the continent. So back when Utah was shorefront property, there seemed to be something separating these populations of dinosaurs or causing them to evolutionarily diverge. That's something that is a relatively recent find. No one really expected this. It was expected that, okay, these are big animals that must have large home ranges. They're just kind of roaming all the way up and down the coast. Instead, there seems to be something, nobody really knows what it is yet. Nobody knows whether this is a mountain range or a river or something else. But by looking at the patterns of these dinosaurs, we're expecting something that's isolating them in such a way that evolution is taking a different path. And it's not just the horned dinosaurs that you see this in. These are dinosaurs from our galleries as well. This is Griposaurus and Parasaurolophus. You find the same genera of dinosaurs up north during the same time periods, but these are different species down south, and this extends to the Tyrannosaurs as well. This is a particular tyrannosaur called Diplodocus that's on display at the Museum of the Rockies. Down here we have Teratophonia, so this is a juvenile and adult of this other tyrannosaur. So same kind of composition of dinosaur groups, same kind of dinosaur faunas, but different genera and different species that are sort of giving us this new indication that something interesting is going on here with the evolution, that the story of why this should be so is still, still being developed. But by naming these dinosaurs and identifying this pattern, we can see that it's there. And the other cool thing about the Grand Staircase finds in the Camarasaurus formation is that as fierce as the Tyrannosaurs look, probably the thing that you'd have to worry about most were giant alligatoids. This is Deinosuchus from the gallery downstairs. So the Tyrannosaurs weren't actually all that big by predator standards. This animal, meanwhile, was about 40 feet long at maximum, and much, much larger. And as researchers here at the museum are discovering, most of the tooth-marked dinosaur bones that people are finding, they don't have the tooth marks of predatory dinosaurs. They have tooth marks of crocs on them. So either through predation or scavenging, it's animals like this are actually sort of the fiercest era. So after this time period, the Earth continued to change. I mean, this is obviously quite a different vision than what we're used to I mean, way back when we had this western interior seaway, southern Utah was a lot more sort of like Louisiana, but with much, much bigger alligators and dinosaurs. Eventually, this started to recede. The environments continued to change. The planet continued to evolve. And we get those really famous charismatic dinosaurs. This is from the Natural History Museum in Los Angeles, Tyrannosaurus. We don't have Triceratops here, but we have a close relative, which brings up sort of one of the, I think, hottest ongoing debates in paleontology right now. And that's whether this dinosaur at the top, Triceratops, transformed into Torosaurus, which is this dinosaur at the bottom. Whether Torosaurus is basically the adult stage of the dinosaur that we call Triceratops. A pair of paleontologists in the Museum of the Rockies, John Scannella and Jack Horner, proposed this a couple of years back, and said, well, very, very late in life, for some reason that we don't really know why, the frill of Triceratops might have expanded and these holes opened in it. Massive transformation, relatively close to the end of the dinosaur's life. Nothing like this has ever been seen before, and the sort of question, and the fossils documenting this exact change have yet to be found. So the question is, well, are these animals really separate, or are these growth stages, and how do you test that? And one of the ways to test that is to look for areas in which you have Torosaurus and not Triceratops, or look for a juvenile Torosaurus specimen that indicates, okay, well, this animal had this kind of anatomy for its entire life, that this wasn't a late life change, that this is something that's relatively consistent. If you look at the way these dinosaurs plot out, you have Triceratops there in gray and Torosaurus in black. Now, among the northern range, they're typically found together, so it'd be, it's reasonable to expect, okay, well, maybe we're really looking at, transformation here. But along the southern range, in Utah's North Horn Formation, about 66 million years old and a little bit older, and in the Javelina Formation in Texas, you only get dinosaurs that seem to be Torosaurus. We don't really know because they're so fragmentary, and it's really hard to tell, are they true Torosaurus or there's something else? But there's a graduate student here, Yale Wiersma, and other paleontologists who are working on this, trying to determine what is the proper name for this dinosaur, and if this really is Torosaurus and there aren't any Triceratops in this formation, that would really underscore the validity of Torosaurus being a real dinosaur. And that has important implications for not only how dinosaurs grew, but what was happening to dinosaurs at the very end of the Cretaceous. I mean, if you look at some of these formations, do you have really 10 different dinosaurs, or do you only have 3 or 5? The way that we name these things and identify species matters in terms of tracking major evolutionary patterns. Unfortunately, all we have are the bones, really, and their tracks and whatever remains in the fossil record. 66 million years ago, an asteroid struck what is now the Yucatan Peninsula, outpouring in the Deccan Traps in India. You had climate change that was already occurring. All these things seem to have conspired together to kill off the non-avian dinosaurs. The avian lineage, birds, survived. Dinosaurs are still with us today. But all the really cool ones, the ones that spark our imagination, my apologies to ornithologists, but things, an Apatosaurus is so much better, I think, than a chickadee. Or, I like penguins as much as the next person, but it can't compete with an Allosaurus, I'm sorry. These are the animals that really spark our imagination. They continue to sort of ask, why are they gone and why were they successful for so long? And why are they still successful? We're looking at a lineage that has persisted for over 245 million years. If you consider the entire range of the human lineage, it's only 6 million. If you want to extend that a little bit further out to primates, it's only about 66 million. So even if we take our sort of most liberal estimate for our group, we still come nowhere close to sort of the dinosaur. I find Utah is a great place to just think about this and why this is. When you're out fossil collecting, you have plenty of time to think. It's just you and the Badlands, more or less. This is a view from the Horse Mountain campsite in Grand Staircase, Escalante National Monument. And the last time I was out there, or no, it wasn't the last time I was out there, but about a year ago I was out there with some paleontologists from our museum and from the Denver Museum of Nature and Science. And as we were walking out to some of these exposures, a paleobotanist on the other crew said, everything that's changing in the world now, especially with human-caused climate change, the way that we're altering habitats, the way that we're spreading invasive species throughout the world, like, why do we do paleontology? There are ways that we can use science to really, help save the world in a literal sense, and yet we keep digging through the past. And he didn't have an immediate answer for that, and neither did I, but it was definitely food for thought as I continued to sort of tromp around the Badlands. And eventually it occurred to me, it's like, well, this is the only record that we have of the way that things like climate change and invasive species have really changed the world. I mean, finding a new dinosaur species or figuring out what color dinosaurs were or figuring out social behavior, how they partition their niches in different ecologies, those one-shot things might not seem particularly important by themselves, but you put that all together and you start to understand how animals evolve, how they respond to changes that are still going on today. So maybe by looking to the past, maybe by using dinosaurs and their neighbors and their relatives and their cousins and contemporaries as proxies, we can start to outline what's going to happen in the not too distant future. Perhaps rather than just being a record of what has gone on, the past could be the key to the future. And we need to keep digging. I mean, if you look at this chart of what we know, there's some time periods that we know quite a bit about. 76 million years ago, Camarasaurus formation, we have quite a few dinosaurs from there. We have quite a few Jurassic dinosaurs. Okay, I have no idea whether. We're getting to questions in a moment anyway, so I'll try and just be louder. There are a few slices of time in here that we know quite a bit about, but there are others that we don't, where they're just a couple of teeth or a couple sets of tracks or a couple bone fragments, where we can get an idea of maybe the kinds of dinosaurs around, but there's still gaps in our knowledge. There's still, most of the age of dinosaurs remains undiscovered. There is an estimate that to date there have been about 500 different genera of dinosaurs named that are probably valid, based upon the number of formations that there are that have yet to be fully sort of investigated or even discovered, slices of time that we're missing. There are probably over 1,800 species of dinosaur or genera of dinosaurs total. So we haven't even begun to approach even just cataloging the number of dinosaurs that there were, much less understanding their biology and ecology and evolution. I mean, we're really just, to use a bad pun in this instance, scratching the surface of the dinosaurian record in a literal and abstract sense. And that's why I'm glad that I'm here, and I'm glad that I'm volunteering with the Natural History Museum of Utah, because this is really undiscovered country. This isn't a matter of in 5 years or so we're going to have all the dinosaurs and it'll be done. We're really just getting started. And who knows what the museum hall is going to look like a century from now. I mean, we have this wonderful new museum, fantastic halls that give us the best image of dinosaurs as we understand them now. Who knows how many other bizarre species or how many other sort of changes to their biology or image of dinosaurs are going to come about if we could sort of time travel a century or two in the future and see what Utah has to offer in terms of dinosaurs. And all of this is a way to say that this isn't just a matter of finding monsters or finding things that really just excite us about the past. I mean, dinosaurs have that aspect to them, but I think by chasing after them, investigating their records and what they can teach us, we can learn lessons about our own history and about the future. I mean, after all, the first mammals evolved about the same time as the first dinosaurs did. And our ancestors and our cousins lived under the feet of dinosaurs. And we often say, okay, well, that asteroid impact that happened, or that mass extinction that happened 66 million years ago, that allowed the age of mammals to start. We wouldn't be here without that catastrophe. And that is true. But at the same time, dinosaurs shaped the evolution of our ancestors for over 160 million years. Dinosaurs made us who we are, and I still think we very much need them. Thank you all for coming out, and let's just talk dinosaurs. Fire away, anything you want to know, yeah.
Are we getting any closer to figuring out what?
Yes.
Changing a little bit.
Sure. So the question was, are we getting any closer to figuring out what color dinosaur skin was? So the progress that's been made through this has actually been done through feathers. So even though not only are birds avian dinosaurs, but many traits that we think of as being bird traits appeared in dinosaurs millions and millions of years. Feathers, pardon me, and their precursors. And the cool thing about this is that if the preservation is good enough, you can take something like a scanning electron microscope, zoom way down onto a fossil bird feather, and you'll see these little blobs that are sort of distributed through the feather at different densities, and they'll have different shapes and different distributions. They're called melanosomes. And these are in modern bird feathers as well. And this is a way that structure creates color. So based upon the distribution, density, and all that cool stuff, light hits it, it'll send back colors like black or red or gray. So even though the fossil itself does not preserve the original color, the color is created through structure. So you can reverse engineer what color dinosaurs were by looking at those feathers and comparing them to those of modern birds that we know the color for. Some people are suggesting that this can be applied to fossilized skin as well. The trick with that is that you need skin that's preserved to that same degree. Oftentimes it's an impression, so it's just in the sandstone. In the mudstone, there's no original skin material left. Yeah, it's just sort of a natural cast of it. But I've heard rumors that this might actually work and that some people might have some results for this. So as long as there's something preserved, as long as there's something to actually look at, paleontologists now start to reverse engineer dinosaur color, which is awesome because as a kid I was told that we'd never ever know. That's one of the things that's the great mysteries that's going to always remain sort of beyond the veil. And so I could, when I used to draw dinosaurs as a kid, I drew one that I colored like a macaw parent, with fire engine red with this white spot. It was absolutely awful. But it was like, well, who could say? It's and now I'd say, no, that was atrocious and totally wrong. Unfortunately, that dinosaur didn't have feathers on it, but if it did, at least get at that question. Yeah?
I'm curious as to what your...
Yeah, so the question is that, so the question was what my opinion is of the Torosaurus Triceratops debate. And I haven't, pardon me, I haven't totally made up my mind yet. It's something that I don't think it's impossible. I think saying, well, we haven't seen this before, therefore it didn't happen. I mean, that's not a good argument. That's not good science. I mean, there are things that surprise us every single day that we never thought would have been possible. But the burden of proof is on the people who are proposing that this change must have happened. They're saying it's this massive change late in life. And they also pair it with this idea of species recognition. So that these ornamental features are a way for dinosaurs to recognize each other at a distance. But why in the world would you basically change yourself that drastically as you became a full-grown adult, well after you're already reproducing? If you want to be recognized as the same species, it doesn't really make a whole lot of sense. So I mean, my take on it is that probably isn't the case, that Torosaurus and Triceratops probably are separate dinosaur genera, but it's not an impossibility that they're the same either. This is the sort of thing. It's when someone comes up with a hypothesis, or unless it's something that's just totally out there, we can't immediately say like yes, no, that's right or wrong. It's like, well, that's an interesting question, and now the fun part is actually digging into the anatomical evidence to figure out, okay, how do we actually test these ideas? And whichever way it turns out, it'll still be important to know in terms of how many dinosaurs do we have? How are they actually growing up? How are these features related to sort of sexual maturity or sort of certain maturity in general? So I don't really know, but it's certainly an interesting avenue of research that extends to many other dinosaurs too. So it's not only Torosaurus and Triceratops, or dinosaurs like one called the Natatitan. That's probably just a big version of a dinosaur called Edmontosaurus, these shovel-beaked herbivorous dinosaurs. There's a small tyrannosaur, people often call it Nanotyrannus. It's probably a juvenile Tyrannosaurus Rex. Most of the focus is right now on these latest Cretaceous dinosaurs, but this applies to everything else. Because really, when you've got a dinosaur skeleton, you have to determine what age it probably is. That's not always typically easy, but traditionally, researchers have said, okay, that dinosaur is small, it must be just a miniature species or a miniature genus. So things get oversplit and then lumped back together, and all of this ties into this bean counting of how many dinosaurs there are is important to set just the very basis. Okay, who's living where and who's eating who, and just need that before you even start getting into these other sort of bigger biological questions. Yeah. So. The question was, what's my opinion on the same sort of idea for Pachycephalosaurus? That one I'm a little bit more liable to agree with. I think the evidence is a little bit better in terms of sort of the bone resorption in the skull and the sort of changes that had to happen, where basically you have these animals that are relatively flat-headed as juveniles, then they develop this thick dome of bone on top of their skull, and they've also got spikes starting out backwards, and then towards the end of their lives, you lose those spikes, and then you have just this bigger, solid dome. I think the evidence for that is pretty good, but it's the same thing with Torosaurus and Triceratops. The number of animals that we're looking at is severely limited. Some people say, okay, well, I know there's a juvenile of this other have the spikier one, in somebody's private collection, but I can't publish on it because it's privately held. I mean, that's why it's important to keep finding more dinosaurs. If we've just got one of anything, we kind of develop this typology. Okay, this is sort of like the archetype for all members of the genus. But I mean, look around the room; we're all different. It doesn't have to just do with age, but it has to do with sort of our genetic background, our bone structure, and all that. There's variation within a species. So the more dinosaurs we have, the better we can get an idea of how individual species vary, changes in growth that would affect how many dinosaurs that we're counting. So I think a lot of this stuff is still relatively open, but of all the cases that have been presented so far, I think Nanotyrannus is a juvenile Tyrannosaurus Rex. That's probably accurate, and I think the Pachycephalosaurs are probably growth stages of Pachycephalosaurus proper. Some of the other ones, time. Yes? Yeah, that's an excellent question. The question was, how do we know where we're going to dig? I mean, the impression I had as a kid was just take a shovel and go in the backyard and turn up topsoil and then you'll get a dinosaur. Unfortunately, that was not true. I was nowhere close to being in fossiliferous beds at all. My grandparents' backyard was not the best place to start with Triceratops. The way that you do it though is first you look at a geological map and you look for rock formations that are of the right age between about 250 and 66 million years old. They're sedimentary rocks, so not rocks that have been laid up by volcanoes, for example. You're not going to find dinosaur bones in that. But rocks that were laid down by rivers or lakes or swamps or even oceans. Sometimes dinosaurs would get washed out to sea and form little reefs before they became buried. So once you've got those identified, you have to do a lot of hiking and a lot of looking. Everybody loves to tell stories of like, well, I was just hiking and I sat down to have my lunch and there was a perfect Tyrannosaur skull right there. It's like, well, yeah, maybe if you're like Phil Curry or Paul Sereno, that'll happen to you. But for most people, you're looking for crumbs. So you're looking for bone shards that show you that there's a fossil nearby and you follow those up and you hope that there's a piece of bone, hopefully mostly intact, that's going into the rock. And from there, you can make, then you have to go into sort of paleo triage. Like, is there too much overburden? Is there too much overlying rock to remove? Is it close enough to get out how hard is the stone? Does this look like a new species or genus or a scientifically significant specimen? Or does this look like just, like a femur that's already mostly eroding away? But in terms of just basically finding them, you just, target the places where you're most likely to find preserved dinosaurs. And you just look for the little bits and pieces that give you some indication that they're there. I keep hoping that that'll work for me. When I went to Grand Staircase, I think last year, you find a lot of, the frustrating part is in some formations, find any scrap of bone, it's a wonderful thing. Like in the Chinle Formation of Dinosaur National Monument, which I spent a lot of time over the past 2 summers with the Natural History Museum crew. Any bone fragment almost, it's wonderful. It's mostly just tracks that we're getting there. So even like a mold of a tooth, perfect. It gives us some idea of who was around. You go to a place like Grand Staircase Escalante National Monument, there's so much bone that you could find, like half of a turtle, and Mike or Randy or the crew chiefs would say, we got like 50 turtles. Like, no, just leave that alone. So it matters where you're looking in terms of what you bring back. But yeah, it all starts with scraps. Yes?
I definitely agree with the fact that how come this semi-circular?
Yeah, so the question was a little bit technical. It was why, if the skeletons that we often call, or they get called sometimes Nanotyrannus, if they're really young Tyrannosaurus Rex, why do they have a different number of teeth in their skulls? Like, why would the tooth count change? And also, why are aspects of the brain and the inner ear seemingly different? Part of that has to do with distortion and crushing, like the original so-called Nanotyrannus skull. It's actually distorted to the side, and the back of the brain is damaged. And that's the only one that really has deserved that name. I mean, there's been talk about Jane, this specimen, nearly complete Tyrannosaurus specimen that's on display at the Berkeley Museum of Natural History in Illinois. That's almost assuredly, definitely a juvenile Tyrannosaurus Rex. In terms of some of the brain stuff, it's very, very subtle. A lot of it has to do with distortion, crushing changes after burial, or just incomplete nature of other things. In terms of tooth count, it seems that in young tyrannosaurs, they're very, very different. So in a young tyrannosaur, you can see this downstairs in our teratophonius mounts, their skulls are relatively long and they're relatively shallow. These animals are not delivering super crushing bites. Their teeth are more slashers than anything else. So these animals are feeding in a different way than the adult animals, because in the adult animals, the skull gets very, very deep. It seems a bit blunter. The teeth get larger. You see this especially in Tyrannosaurus Rex, where even in specimens like Jane or some of these other younger tyrannosaurs, there's a change in tooth morphology that happens. And that might seem very, very strange to us. I mean, we've got no teeth and we have adult teeth and that's it. This seems to be a case of major change where you're going from knife-shaped teeth to larger teeth, and those larger teeth, there needs to be room to house these things. So as they're getting bulkier and as they're getting larger, it's changing. And Tarbosaurus is not Tyrannosaurus Rex per se. It is a closest relative, but it's not the same thing either. So it might be a decent, it's something to judge it against, but at the same time, it's the same problem with saying that, Torosaurus can't be an adult Triceratops because we've never seen this before. It's like, well, lots of things we haven't seen before. Just because we haven't seen it before doesn't mean it's not necessarily true. It's how do we actually go about testing this? So, so far, I mean, honestly, I think people who think that Nanotyrannus is a valid genus of dinosaur, the onus is on them to actually do the work. I haven't actually seen very much research done. There's one paper by Larry Whitmer and his group where they took a CT scan of the skull, and they said, okay, there are a couple of features that might make this valid, but we're not really sure. People like Peter Larson and Bob Bacher, who are really behind Nanotyrannus, they haven't really actually done the work yet. People like Thomas Carr and other Tyrannosaur experts who have actually published on this stuff and looked at Tyrannosaur ontogeny, they seem relatively certain that these smaller animals are Tyrannosaurus Rex. So, I mean, people are going to disagree. It's an ongoing sort of debate. How much did dinosaurs actually change throughout their lives? But at least for now, I'm on Team Tyrannosaurus Rex. I'm sorry, I have to cut you. I have to leave this open to other people. Yes, sir. Yeah. Okay. So the question is, what causes rings that you sometimes see in dinosaur specimens? Actually, those are real bones. So this is not in mammals. This is only in some reptiles and amphibians and fish. But these are actual bony structures that support the called sclerotic rings. And there's actually some debate about whether paleontologists can use these to tell whether dinosaurs were active mostly at night or during the day. Like if you have a larger sclerotic ring with a larger aperture in the middle, that might be indicative of an animal that needs to bring in more light and therefore might be active at night rather than during the day. Whether that's actually true or not, we have to look at modern animals to determine that. But those are actually real bony features, and it seems unusual because some museums have them and some of them don't. And sometimes you see them in restorations and sometimes you don't. But those are actual real bones that's common amongst reptiles, and we as mammals just don't have it. Yes? Yeah. Question was, what's my idea, or what's my take on sauropod dinosaurs shown with spines on their back? That was something actually I thought about when I was helping design this cover, because these sort of bony projections, you might have seen them in the Walking with Dinosaurs documentary and some other restorations. It's on the dinosaur Diplodocus, typically. There's a paper by an artist named Stephen Serkis. He runs the Dinosaur Museum in Blanding. He wrote just I think 2 papers about this, relatively short, just saying, I found the spine, it seems to be associated. There's a pretty decent chance that that's accurate, but nobody has found these in place yet, in the way that people have for bony armor of Ceratosaurus or some of these other armored sauropods. So we're still waiting on something with these spines articulated. It's certainly possible, and I went back and forth about this for my own, book cover. The artist eventually decided to go against it, but we do know that sauropods are much more highly ornamented than we often think of them being. Not every single one was, but there are sauropods that, especially these Titanosaurs from South America, that had armor all over the backs, and they had tail clubs or they had spines sticking out of their necks. So even though our classic Jurassic dinosaurs are sort of the epitome of sauropodness, they're actually much more varied and a lot weirder than we ever really expected. Yes, sir.
Other than the cladistic of dinosaurs, what would be your big question as dinosaur paleontology? What has to see climate change? Questions that studying dinosaurs can reveal still.
So the question was, what are the big dinosaur questions that still need to be answered? A lot of it has to do with the basics of their biology. So looking at an animal like this, like Apatosaurus, how much did it need to eat during a day? That's something that has to do with physiology, something that, that was this catalyst behind the Dinosaur Renaissance in the 1970s, where they ectothermic, or like modern reptiles, their body temperature varied with that in the environment. Did they maintain high constant body temperature, so being more like mammals or birds? We just don't really know. It seems the bulk of the evidence seems to indicate that they were much more like mammals and birds. But I mean, telling a dinosaur's temperature, unless you've got a time machine and a thermometer and a lot of bravery, we're not going to really know that. And that has important implications. At least coming up with a general physiological profile give us some indication. Okay, how fast were these animals actually growing? How much did they need to eat? How fast did sort of ingested material go through their systems? Were animals like this, hindgut or foregut fermenters? What sort of system did they use? Even how much blood pressure? How did they regulate their blood pressure in order to get blood from that? Must have been a massive heart all the way up a neck that's 20, 30 feet long, and back again. And conversely, how do you prevent blood from pooling in limbs that are over 12 feet high? You might get edema if blood starts pooling and stuff at the bottom. Horses and other animals today have got special adaptations where when they step down, it helps push blood back up, the blood vessels back towards the heart. We don't know whether dinosaurs had this or not. So in a lot of ways, some of the most basic questions about dinosaur lives are the ones that are the most perplexing, because they relate to soft tissues or other lines of evidence that we don't necessarily have directly. My favorite one, though, in terms of debates that are going on now, has to do with sexual dimorphism. So this is the idea that male and female dinosaurs, beyond their sexual organs, would have been different. So sort of the ornamentation on something like Stegosaurus or Triceratops would have been different among males and females. So far, no one has been able to convincingly demonstrate sexual differences of this sort among dinosaurs, which is really kind of weird, because these are complex animals. We assume they have complex social behavior. We can't, we can imagine, but we have no direct evidence for mating dances or mating systems or leks or anything like that. But that's odd that you have animals that are ruling the world for over 160 million years, and the males seem the same as the females. So it's either a matter of we just don't know how to detect this yet, or they actually weren't. And what this might say about sort of mate choice and sexual selection and how dinosaurs went about making baby dinosaurs. So again, it goes back to these very basic biological, like we know that dinosaurs had to do these things. We know that dinosaurs had to mate and must have had some way of picking a good one from a bad one. But how did they actually do that? See, that's the stuff that keeps paleontologists up, awake at night. The sort of things, not just where am I going to find a new dinosaur, but just how did these animals actually live? I think that's part of their enduring appeal, because we obviously just we don't know. Yeah. Yeah.
From Texas to Utah.
Mm-hmm.
Was it the earlier?
Okay, so the question is, there's a really huge sauropod dinosaur, relative of Apatosaurus, called Alamosaurus. And it lived, when did it live? Was it earlier in the Cretaceous or at the very, very end? So this is a terminal Cretaceous dinosaur, so 66 million years ago, and a little bit earlier, around 70 or so. You find parts of this dinosaur in Texas and New Mexico, and I believe in southern Utah as well. And this is one of those things that also just challenged my perceptions of dinosaurs as a kid, because I was told that there was a sauropod hiatus. So you had scenes like this. You had Apatosaurus and these other giant sauropod dinosaurs. Their heyday was in the late Jurassic, and then they all disappeared from North America, and that was it. They just they got replaced by horned dinosaurs and hadrosaurs and things like that. Finds in South America and Africa and Asia and elsewhere have shown that, well, yes, they did sort of die back in North America for a few million years, but then you had this reinvasion of North America by these super titanic sauropod dinosaurs, among the largest that ever were. So Alamosaurus was a dinosaur that might have been in excess of 100 feet long or so, that, this was living alongside Torosaurus and Tyrannosaurus Rex. So it actually kind of saves a childhood dream, not in a direct way, but you often, as a kid, I would often play, and I imagine many of you did as well, with your Apatosaurus or your Brontosaurus toy and your Tyrannosaurus toy. And these dinosaurs never actually met in terms of the timeline. We live closer in time to Tyrannosaurus Rex than T-Rex did to Apatosaurus. I mean, there's 66 million years between us and Tyrannosaurus Rex. There's over 80 million years between Tyrannosaurus Rex and Apatosaurus. So, I mean, you could fit, the whole age of mammals within that sort of time frame. But because we have Alamosaurus making its grand reintroduction into North America, we can now imagine, Tyrannosaurus Rex going to town on one of the necks of, a dinosaur, quite like this. So, if you ever have a child or a niece or a nephew or a grandchild, playing with the sauropod and the Tyrannosaur in the sandbox or elsewhere, don't discourage them. Just make sure they get the names right. Yes, sir. To what? Oh, absolutely. So the question was, are there ways to sort of study the biomechanics of dinosaurs, the motion, the way that they move, the way that they walk? And this is actually a very big research program right now, is reconstructing the muscles and determining sort of what their performance, their performance as animals, walking, running around. I'm actually working with a paleontologist at the Museum of Nature out of Berlin on dinosaur mating, what positions would have actually been possible from a biomechanics perspective. And so he took laser scans, basically. So this is actually a good example. This paleontologist, Heinrich Morrison, he had taken laser scans of the stegosaur called Kentrosaurus. So think of Stegosaurus, and rather than plates going down the latter half of its back, have spikes, including 2-foot-long spikes jutting out over the hips and stuff. Really a gnarly looking dinosaur that you certainly wouldn't want to rub the wrong way, especially for a possible mate. So he took laser scans of this, and he tried to determine, so could this animal rear back onto its tail, like you sometimes see in restorations, because stegosaurs take up this tripodal stance to feed up high. And how fast could it swing that tail in sort of its own defense? I forget the actual speed, but he wrote in his paper that it was enough to drive one of those spikes through, all clear through a human skull, basically. So quite a powerful swing on this dinosaur. So using that for defense, and then I figured, well, people have been wondering about dinosaur mating for a number of years, and they usually just commission an illustrator to make a two-dimensional sketch of whatever. But it's easy to figure this out on paper, in 3 dimensions. Obviously the dinosaurs figured it out, but can we reverse engineer this using these models? So I very delicately asked him, could you make a double of your laser scan skeleton, position them just so? So that's what we're working on right now, is trying to figure out how this actually worked. In a less sort of silly way, I mean, people have done this with things like finite element analysis. This is something that you see in engineering a lot, determining sort of the breaking point of various structures, like given certain pressures or constraints, when and where are they going to snap under which conditions. So you can use this for things like a Diplodocus skull. You can determine if they're scraping sort of bark and branches with their teeth, or were they just nipping leaves? It seems like their skulls couldn't handle the stress of dragging those pencil teeth over tree bark. Instead, they had to sort of nip things. In other aspects, Tyrannosaurus Rex has only gotten scarier because of these sorts of studies. So you look at a T-Rex head and you say, yeah, that is nightmare fuel 100%. But sorry. I'm coming off of a flu, so I'm a little bit. How did this actually work? Well, by using biomechanical principles, estimating the musculature and how that would have worked, and the contractile forces and things like that. Paleontologists determined that an adult Tyrannosaurus Rex had a bite force of about, I think, a little bit in excess of 12,000 pounds. So basically, as heavy as a Tyrannosaurus Rex was. So if a Tyrannosaurus Rex stepped on you, it's the same amount of force that it could basically bite with, as well as the strongest bite of any terrestrial predator that we know of. But it doesn't really stop there. In a study that was done on neck muscles, they also, a different team of researchers determined that a Tyrannosaurus Rex should take a 150-pound chunk of meat. I mean, I'm more like 200, but I wish it was 150. But if you imagine, someone about my size, more or less, it could take that, throw them up into the air about 15 feet, and catch them again, and swallow them. This is a behavior called inertial feeding. It's absolutely terrifying. Birds do it, and crocs do it today. We don't know for sure whether Tyrannosaurus Rex did, but it's certainly capable of doing this. So in the original Jurassic Park, when that Tyrannosaur eats the lawyer, rather than shaking its head side to side like a dog, it probably would have trucked him up into the air and caught him again. Like I said, dinosaurs are only getting more interesting and scarier as a result of these sorts of studies. Yes? Yeah. The question was why, from perhaps a biomechanical perspective, were so many dinosaurs bipedal when that seems to be a relatively rare thing today? Part of that has to do with their size. I mean, many dinosaurs, although we celebrate the huge ones, are relatively small, and they came from ancestors that carried their limbs beneath their bodies, and it was relatively easy for them to get away with being bipedal. I mean, once you start to build up skulls or musculature, you need a big sort of gut to ferment a lot of vegetative material. That starts to put different constraints on sort of balancing. From a biomechanical perspective, I mean, the quadrupedal dinosaurs are typically herbivorous ones. There were no carnivorous dinosaur quadrupeds that we know of. It seems to be more of a matter of contingency and ancestry, is that very early on, earliest dinosaurs were these bipedal omnivores, or at least they're descended from them, and they just kind of kept that thing going. It's a matter of speed and walking efficiency. Well, just you've got 2 legs to sort out instead of 4. Silly in a scientific argument, but yeah, I mean, bipedalism isn't necessarily there to. I mean, we do it, even though they walk on all 4s most of the time. Our closest 8th relative doing it as well. It's more of a matter of context and Okay, so question was, there's an ongoing debate in the media that Tyrannosaurus was, over whether Tyrannosaurus Rex was a predator or a scavenger. And I stressed in the media in that setup because that's the only place it actually exists. There's no academic debate about this whatsoever. So I think it was 1993 or so, Jack Horner of the Museum of the Rockies, he gave a talk about Tyrannosaurus where he suggested at this sort of public dinosaur symposium called DinoFest, suggesting that Tyrannosaurus Rex might have been an obligate scavenger. So it was basically the Cretaceous cleanup crew, just kind of eating whatever it could that had already died. And this was an idea that had been proposed decades before by another paleontologist for Tyrannosaurus named Lawrence Lamb. He came up with a similar idea. But there's no real science behind this. I mean, Horner said that, okay, Tyrannosaurus seems to have small arms and small eyes, and it's got a big heavy skull, and it's got these heavy teeth. This seems to be an animal that can crunch through bone, but maybe it wasn't running that fast, or it's not something like a velociraptor that looks like an active predatory animal. That we actually have fossils. There's one of a velociraptor and a Protoceratops are locked together that some people have inferred predation event. We don't have anything like that for so maybe it was an obligate scavenger. They didn't do any follow-up on this, and since then, paleontologists like Thomas Holt, a Tyrannosaur expert, he wrote a response sort of looking at all these features that Horner proposed. None of this would have prevented Tyrannosaurus. So it is probably very much like hyenas live today, and that it wasn't really using its arms at all like prey capture, just the difference between hyenas and lions now, where lion has these arms that can sort of pronate and grab. That would be something in the past equivalent to Velociraptor, whereas a hyena, it's not doing that. It's just using its skull and this bone-crushing ability. And yet, despite the fact that it can't grasp, there are some populations that get over 96% of their meat from hunting. So even though they're traditionally cast as these gnarly kind of scavengers, they're actually quite efficient hunters that lions are kind of kleptoparasites of and steal prey from. So just having a big, heavy head and small arms doesn't make you automatically a scavenger. So the short answer to all this is that Tyrannosaurus Rex almost certainly did both. And there's actually osteological evidence for this in the fossil record. There's at least 2 hadrosaur specimens that have bite wounds on them that have healed that could have only been made by Tyrannosaurus Rex. That's the only large predator during that time. So these failed attempts actually show us that this Tyrannosaurus tried to eat these animals, didn't succeed. And then on top of that, there are other specimens like a Triceratops pelvis and a few others that have these big tooth gouges in them that seem to after death. We can't say whether that Tyrannosaurus killed this animal or not, but we know it certainly was capable of dismembering a carcass. And on the flip side of this, I mean, Horner would often cite Velociraptor as like sort of the epitome of a predatory dinosaur, but we actually have evidence now that Velociraptor scavenged as well. There are bones that have been found in Velociraptor gut contents that seem to have been, from animals. There'd be no reason for it to swallow bone off some of these creatures that it had been feeding on unless all the flesh was basically gone already. So it probably just happened across something and just swallowed whatever was left. And we can see this in terms of the bone damage and the bone weathering in its gut contents. So most predatory dinosaurs, in fact, they're probably like predators today. They did both. They're perfectly capable of hunting, but they wouldn't pass up a free meal. Yeah. Mm-hmm. All right, can we take just one last one? Just one more. Yeah. Yeah, I'll try and make this a quick response. The question was, do you have any evidence that dinosaurs suffered from disease or parasites or other sort of injuries? And it's quite good. I mean, the trackway near Moab, that's a limping allosaur, or it's a limping large theropod dinosaur, so that seems to be a case in the track record. And it meshes well with the skeleton that's, I think, at the University of Wyoming, now called Big Al. So this juvenile Allosaurus that has, I think, over 17 different pathologies on its skeletons. Broken finger bones, broken ribs, really bad inflammation on one of its toe bones. So on many dinosaur skeletons, if you know what you're looking for, you can actually find a lot of healed breaks and other pathologies. My favorite example is actually in the jaws of Tyrannosaurus Rex. So if you look at Sue, the famous T-Rex, you'll see all these holes in her lower jaw. It looks like someone unloaded a shotgun into her jaws. For a while, paleontologists thought that this was a matter of a rival Tyrannosaur coming along and biting her on the face. We know that Tyrannosaurs fought like this because of pathological specimens that have healed. People thought that this might have been a fatal case, a rival coming along and killing her at the very end of her life. What actually turned out to be the case was that these holes are smooth-sided, and they correspond very, very well with damage that we see in modern birds and pigeons and hawks today. They're infested by a microorganism called Trichomonas. And these microorganisms, when they infest an organism, they'll create ulcers and lesions and actually eat into the bone and create these smooth-holed sort of smooth-hold damage. So really one of the largest terrestrial predators of all time was probably killed off by an organism that you couldn't even see with the naked eye. I mean, Sue, the Tyrannosaurus Rex, probably couldn't drink or eat anything. At the very end of her life, it was probably killed by starvation. So through these signs, if you know what to look for, you can not only identify the pathologies, but specific sort of life events in the lives of dinosaurs. And that's why I kind of love pathologies, even though they're kind of, the stories can be kind of sad, but they really bring fossils alive in a way that you can look at just like a femur or a skull or something and say, okay, well, that's just an old fossil. It's been dead for millions of years. But when you can identify these pathologies, you can trace it back to, and really get a sort of high-res picture, in a way, at least in your imagination, of very specific things that happened to dinosaurs during their life.